Matter and energy. Today we're going to focus on motion graphs and energy transformations. You have a study guide here. It's hyperlinked. It will bring you all to the study guide on energy and motion. So today we're going to look at energy transformation. All energy forms and energy transformations can be traced back to the energy of the sun. The law of conservation of energy states that energy cannot be created or destroyed, but it can change from one form to another. For example, potential energy can be converted into kinetic energy as a roller coaster moves down a hill. So if we look here, we can talk about energy transformation, some examples. So if we have a flashlight, the energy would be chemical because there are batteries involved inside the flashlight. So chemical is a type of energy. You find it in food, batteries, it's stored energy. Well, that battery, that chemical energy is transferred into electrical energy. And then the electrical energy is transformed into radiant energy, the light that we get from the flashlight, and then eventually thermal energy, heat. Let's look at the example of a hairdryer and talk about the energy transformations. Well, a hairdryer we must plug into an electrical socket, so we know that's electrical energy. Okay, that electrical energy then gets transformed into mechanical energy, energy of motion, because the fan inside the hairdryer moves. Then that mechanical energy gets transferred into thermal energy, which is heat, which dries your hair, and then eventually sound because we hear it. So what are the types of energies that can get transformed from one type to another? Well, Mr. Sense will help us remember those. So M is going to stand for mechanical. Anything that moves would be mechanical energy. Radiant energy would be light, like the sun or a light bulb. Chemical energy would be stored energy, like food, gas, batteries, any type of stored natural resource. Electrical is where you plug into an electrical socket with a wire. Nuclear energy, thermal energy, heat, and sound energy, what we hear. Okay, before we talk about energy transformations, we're going to look and graph changes in motion. So let me grab some wet paint so I can explain. So here it's telling us that a student slid a small wood block along a flat tabletop for a distance of 1.6 meters. The data show the motion of the block of the wood. Which graph displays the motion of the wood block? So first of all, what you want to look at is your data. So here in the table, we have time and speed. Remember, speed equals distance divided by time. So this is a speed time graph. Okay, so as we look at the data here, we can see that our time is increasing from 0 to 0.2 to 0.4 to 0.6 to 0.8 to 1. So as our time is increasing, what's happening to our speed? Seems to be going down. So I'm decreasing my speed as time goes on. So let's look at these speed time graphs to see as time increases, my speed is going to decrease. So here, what you have here for your speed time graph, time is increasing on your X, but look at your speed. Your speed is increasing. So this is incorrect. If we look at B, it's actually the same graph, so we can cross this one out because time is increasing and your speed is increasing. I'm going to cross that one out. Here, as time increases, your speed is constant. It's the same. Okay, so this flat line is telling you that there's a constant speed there, so we can cross that one out. So our answer has to be D. So let's have a look. So as time is increasing, what do we see? Well, we see that our speed is decreasing. Okay, so this graph represents that data table. Okay, so here, let's drag and drop these labels into here. Okay, so maybe what I can do is get rid of my web paint and just drag and drop. So from line A to B. So from line A to B, you see that the slope here is very steep. So this is where you're going to have a fast, constant speed. Straight lines like this are telling you about constant speed. But again, before we talk about speed, make sure that you look at your x-axis. You have time increasing from left to right. Then up here, you have your distance increasing. So this is a distant time graph. It's a little different from what we just saw on the last slide. Okay, on the last slide, let me just go back up here so you can see that this is a speed time graph. Okay, but now we're looking at a distant time graph. Okay. So what about line E through F? Line E from F, you're having a constant speed, but it's not as fast as this one because this is a steeper slope. So I'm going to say constant speed from E to F. So let's drag this one over. Okay, and then from line H to J. From H to J, this means you're going back to where you started. Okay, so it's returning to the start, because here you're leaving your starting position. Okay, but when you go back that way, you're returning to your start position. And what about D to E? So D to E, what you have here is your time is going by, but you're not increasing your distance. So you're resting, you're stopping. So pretty much kind of you were returning back to your original, but then you stopped and you rested, and then time was just going by. So you stopped to rest at a distance of 15 meters. Okay. Here we have some scenarios, and we're going to try to match them. So I'm going to read the scenario and then see which one it best matches. Okay, so Racer freaks out about a pie in his face. Not being able to see, he returns toward the start for 1 second. So remember, when you return to the start, you're going back from where you came from. Okay, but we only go for 1 second. So here's time 1 second. Okay. And so that would be H to J, which is not an answer choice. So let's go back. Okay, so maybe it's C to D. Okay, so from here to here, the racer freaks out about the pie in his face, not being able to see. He returns towards the start for 1 second. Okay, let's read the next one. Racer starts off running with a fast, constant speed away from the start for 25 meters. Okay, so that looks like A to B, and we do have that choice. So from here to here, remember, you're running really fast because the slope is steep, and you're constant because of the straight line. Okay, and we're going from 0 to 25 meters. The racer is more careful now, running at a slower, constant speed, looking out for hidden dangers. Okay, I'm going to say E to F because it's not as steep as this slope, and it's constant. And then here, Racer gets hit in the face with a delicious pie, making it hard for him to see, so he stops running for 2 seconds. A flat line on a distant time graph is telling you that they're resting. Time is going by, but you're not increasing your distance. Okay, so let's have a look at these distance time graph. We're going to drag and drop the motion descriptor cards to the table that describes the motion for each graph. So I'm just going to kind of grab it down here and read it and then decide which way it goes. A student runs 2 minutes around a running path. The student completes the first lap in 20 minutes. Okay. The student then sits on a bench and rests for 5 minutes before completing the second lap in 25 minutes. Okay, so what I see here is this graph over here, because here we are the first lap in 20 seconds. So look at your time, okay? And then after that, we rest on the bench for 5 minutes, and then we complete the second lap in 25 minutes. So let's read this one and see where it goes. A toy train moves forward at a constant speed, slows down, and then stops. So this would be this graph here, because you have a constant speed here from here to here. But then when you start to have a curve, it means you slow down. So I have a constant speed, curve means I'm slowing down on a distant time graph, and then a flat line means I am stopping. Okay, so I'm not going any further, I'm not going any more distance, and I'm just resting. Okay, so again, it's a distant time graph. So this must fit here. So let's read and observe the graph. A student walks 1.5 kilometers to a friend's house in 20 minutes. Then the two students then walk another 1.5 to school in 40 minutes. Okay, so remember, you only want the time from here to here, so that would be 40 minutes. I can demonstrate energy transformations, such as the energy in a flashlight, where it changes from chemical to electrical. So the blades of a wind turbine are at rest until the movement of the air causes the blades to spin. So what's the energy transformation? We're going to drag and drop here. So here you have a wind turbine, it's at rest. So what you have is mechanical energy, energy of motion, that's going to turn into electric energy so we can turn on our lights. So what we're looking at is mechanical energy to electrical energy. Okay, here we're going to drag and drop correct form of energy and label to identify the energy transformations occurring in the picture. So here we have light energy. So light energy we call radiant energy from the sun. Radiant energy is going to get transformed into chemical energy, food. Here is a picture of a brain. So what we have here is mechanical energy, energy of motion, because he's moving. And then that's mechanical energy is going to get transformed into thermal energy, to heat energy. So here we have a fire. So we want to look at thermal energy, because it's giving us heat. Okay, and then from the heat, we're going to get light energy, radiant energy. Here we have solar panels. Those solar panels from the sun's solar energy is going to give us electrical energy so we can turn on our lights at home. Okay, here we have a pencil sharpener. So it's an electrical pencil sharpener. So we need electrical energy because we're plugging it into the electrical socket. And then that's going to move. So that's going to be mechanical energy to sharpen our pencil. Here we have chemical energy, which is food. That chemical energy is going to be transformed into heat energy to keep our body temperature maintained. And lastly, I would like to just discuss these visuals at a class. So from here, what we have is chemical energy to, we're going to do it backwards. I apologize. Mechanical energy, we're striking the match on the box, into chemical energy because we have that stored energy. Here we have thermal energy, heat energy, which is going to get transformed into chemical energy, food for us to eat. Here we have electrical energy being transformed into chemical energy. Radiant energy, the sun, is being transformed into chemical energy. Chemical energy in the leaf is going to give us chemical energy food. Down here, what we have is mechanical energy, the spinning of the windmill, which is going to give us electrical energy. At the microwave, we plug it in, so that's thermal energy being transformed into electrical energy. So here we have electrical energy being transformed into electrical energy. It's a transformer that will enable us to turn on our lights. Here we have radiant energy because it's solar, and then that solar energy is going to give us electrical energy. And then lastly, chemical energy is a battery, and that's going to be transformed into electrical energy. Lastly, I would like to go over this diagram. It was a STAR test question. We're going to fill in the blanks. So it says, some of the chemical energy in the natural gas in the stove transforms into thermal energy, which is going to heat the water. Then some of the thermal energy changes into sound energy when the water forms steam and the steam leaves the kettle. So what type of energy do we start with? Then it gets transformed to what type? And then lastly. So here with this sentence, we can say we're getting chemical energy from the gas stove. Okay, that gets transformed into thermal energy, heat energy to heat the water. Once the water is heated and leaves the tea kettle, you're going to have sound energy. Okay, I hope you enjoyed your lessons on energy transformations and distant time graphs.